Math is so innocent, and let me show you in that in this video. And this problem was from Ovidiu Furdui of Romania in the School Science and Math journal. So basically, I have a double sum over here, and you might have seen a similar kind of sum. Um, let's say sum from t equals to 2 to infinity zeta of t minus 1 by t. This sum is in Wikipedia, and also it has been proved by Math 505, and the proof is over here. And this is actually equal to 1 minus Euler-Maston constant. But over here, it's somehow different. There's m plus n instead of t. And how do we manipulate this sum to get in this form? That's the real question for this problem. And for now, how will we try to see this is? We will try to hack this problem. So basically, let us try to see how the values of m plus n are. So basically, if we let t as m plus n, yeah, let us try to see how many times m plus n will be 2. Yeah, okay, this value will be 2. So basically, one of the cases when there is 1 1, and only that is the case. Okay, for 2, for the sum to be 2. Now let us try to see how many times this sum will be 3. So basically, when there's 1 and 2, and when there's 2 and 1, so there are 2 times when this sum will be, when this m plus n will be 3. Now let us see when the m plus n will be 4. So basically, what we can now do is 1 times Riemann zeta of 2 minus 1 by 2 plus, now there's 2 times, yeah. So 2 times Riemann zeta of 3 minus 1 by 3. We can work case by case, yeah, because we are not missing any cases, so the math should work, yeah, because if we are containing all in some different ways, but we are containing all, so that should work. Now for 4, there are either 1 comma 3 or 2 comma 2, and basically the values for m and n, and basically 3 comma 1 when m is 3, n is 1. Yeah, basically there are 3 ways. So basically plus 3 into Riemann zeta of 4 minus 1 by 4 plus. And if you continue it like this, let us see when t is m plus n is 5. When is this 5? Basically, there are only 4 ways. We can notice the pattern clearly. 1 comma 4, 2 comma 3, 3 comma 2, and 4 comma 1. Basically, when m is 1, n is 4, m is 2, n is 3, m is 3, n is 2, m is 4, n is 1. Basically, over here, when for the 5, m goes from 1 to 4 only. So basically there are 4 ways, and for t there are t minus 1 ways. But okay, so let's go write 4 times Riemann zeta of 5 minus 1 by 5, and basically for nth term there are n minus 1 times Riemann zeta of n minus 1 by n. And if we sum all this, we should exactly get this sum, because we have now exhausted all the possible cases. We have now have taken care of all the cases, yeah, that might arise over here. Basically, the sum will just begin from 2, and when it goes up and up, we have known how many times does that sum occur. So now we can write this sum as in this equivalent form. Basically, sum going from this t going from 2 to infinity, yeah, and there are basically t minus 1 times this sum appears, Riemann zeta of t minus 1 by t. We are basically writing this sum over here in the notation form, yeah. And now we can have this form. Let's see how. First of all, let us break this into 2 sums. When we multiply this by t, we get Riemann zeta of t minus 1, and then minus sign and multiply by 1. The Riemann zeta of uh, 2 to infinity, and now 1, no change, Riemann zeta of t minus 1 by t. Okay, multiply by t cancel out, and this thing. Now I've already proved in my one of my videos already that Riemann sum from 2 t equals to 2 to infinity, or Riemann zeta of t minus 1. This is actually, surprisingly, this is equal to 1. I have, like, this is so amazing because the Riemann zeta of values of 2, 4 are in terms of pi. Yeah, and the sum will be 1. Okay, nice. And I have proved this in this video over here. And this is also proved by Maths 505. Like, I have already linked the video. And this was proved by me. But not basically me, it's from others' proof. And these two are already in Wikipedia. You can check over there as well. Now we know that these two are just some famous sums. And this sum over here is actually 1. This sum over here is actually 1 minus all Masoni constant. So that's why it's such Masoni constant. So basically, like, what I wanted to show you is that you can manipulate maths in any way, and if that's supposed to be true, that will be true. Because like, maths is so innocent, and it will never lie to you. Because if you are doing correct, you have to get correct answer. And that was it. We just manipulated this sum and used standard formulas. And you can also prove these two. This one is really easy. This one might be somehow complex to prove, but you can do it. Yeah, it's not undoable. And yeah, his proof is also really elegant, where he uses di-gamma functions and other product of zeta and gamma. That's cool. Okay, so hope you enjoyed the video. Thanks for watching. Look forward to seeing you in the upcoming videos too.